Cool. Well, welcome everybody. Thank you for turning up tonight. Just before the talk starts, just a quick show of hands. Who's actually using Elasticsearch now in kind of production environment? Okay, so that's maybe 40%-ish. Okay, cool. Okay, just a quick background. We've recently changed our name. We used to be Elasticsearch, now we're Elastic. So what we are, we manage these open source projects: Kibana, Elasticsearch, Logstash, ES Hadoop connector. But we're also a commercial organization now, and we offer some commercial products maybe you're not aware of. So we have Shield, which is our security plugin, Watcher, which is in beta right now. That's our alerting capability, so it can schedule alerts in the system. Marvel, which is our monitoring tool. It's a web component. We recently acquired Found, which is a Elasticsearch hosted service. And obviously we do training, support subscription. Okay, let's get started. Okay, Elasticsearch. What is Elasticsearch? It's a fully distributed search engine. It was built from day one to be distributed, and that's a clear differentiator of the product. It wasn't a bolt-on, it wasn't thought afterwards. It started from day one, distributed. It's schemaless, JSON-oriented, API-driven, and it performs real-time searches and analytics across your data sets, okay? And it's horizontally scalable. So these are kind of key characteristics that people have been interested in Elasticsearch. So this talk, I just wanted to kind of approach kind of three aspects of Elasticsearch, just to give you kind of a feel if you've not used it, or just kind of review some of the features. Terminology. Everybody's got their own terminology. We have terminology, we mentioned nodes. Okay, node is a JVM process running Elasticsearch. It's normally a single server, but obviously sometimes when you have larger servers, you can have co-locate some of these instances. So a shard, it's kind of a unit of work. It's a fragment of your data, okay? Lives on one physical node, happens to also be a single Lucene instance. Index. This is what you'll talk to, okay? You don't talk to shards, you talk to indexes. It's a logical namespace for one or more shards. And when you index a document, we determine which shard gets distributed to that data set. Some other terminology. Segments, okay? When we're writing data into Elasticsearch, we're writing it in segments, okay? So the segment is a Lucene segment. It's a sequential piece of data that is effectively flushed down to disk and then becomes available to search. So as you write a segment, they start joining into a shard, okay? And it's this process that gives you the real-time characteristics in Elasticsearch, okay? Just writing individual segments, write them into the disk, join the shard, become searchable, okay? So that's unit of work. Any shards maketh an index, okay? So that's kind of terminology we work with, okay, in terms. So Elasticsearch is not scaling up, it's scaling out, okay? So there are many advantages to scaling out, okay? So we'll just go through some of them. So you've got yourself your Elasticsearch instance up and running, yeah? You want to get started with it. So we need an index first to start indexing data into it, okay? This index will contain either primary and or replicas, okay? Key characteristic here is a document can only exist in one primary shard, okay? And this is what we call, I guess the definition would be called defining a sharding policy for your documents, okay? So here we are, we're starting up. If you don't have an index called logs, one will be created, and this will be your sharding policy, okay? I'm gonna have 3 primary shards, 1 replica, okay? What does that look like? So you start your node up. This would be what it looked like, okay? You've got one node started. and it's allocated 3 primary shards. Okay. It's also created the loneliest cluster in the world. It's a 1-node cluster. But yes, it has created a cluster. And the key thing here is that every cluster needs a master. There's only 1 node that gets elected as a master. Okay. So what can you do? You might notice also that our replicas haven't been allocated at this point in time. Okay. Elasticsearch knows that you cannot allocate replicas of your data to the same node that contain the primary. It's going to hold them back. They're going to be unallocated. They're just going to wait for more resources. Okay. So spin up another disk. Up comes another node. All it has to have is the same cluster name and be on the line of sight for Elasticsearch. They will join together. When the node comes up, it will request to join the cluster. Okay, it'll either use one of the discovery mechanisms, unicasts, so it'll either have a seeding of some nodes in the system, which then it will ask to join, or multicast if you're able. And the key characteristic here is that obviously as you start up this second node, Elasticsearch goes, hey, I can now allocate my replica shards onto that node. Keep on going. So as you scale horizontally, what Elasticsearch is going to try and do, it's going to try and distribute that data evenly. It's going to try best effort to make sure that the resources associated with this data set are evenly distributed. So you see here that some nodes are primary nodes, so the P1s and P2s, and P0 is moved off onto another node. Replicas are shuffled around a little bit here, okay? So it can be slightly different for each implementation. And this is all done automatically, okay? This sharding policy you asked at the start, that is it. You've asked Elasticsearch now to manage this for you, okay? Now, the number of primary shards is fixed at the time of creating that index, okay? So we said 3 primary. The number of replicas, though, is dynamic. You can ask in real time, okay? So what you can say, you can just dial up and you say, I want more replicas of my data, okay? Why would you want that? So there's an aspect here is that the number of primary shards is kind of your scaling your writes, okay? More primary shards means potentially more write throughput, because those shards will then distribute across physical machines. Those physical machines be written to concurrently, and hence be able to scale writes. Replicas, in fact, are scaling reads. Okay, you're under load. You've got a vast number of customers have just arrived. Prime example here, as we use, is like the Guardian newspaper. Okay. When they've got Elasticsearch monitoring all their articles, okay, and when they realize that this article is going to be of great demand within an infrastructure, they spin up another AWS node, increase the replica count, go across that bump in popularity because they've now scaled the reads. Popularity, if that article drops off, they scale it back again. So it's elastic, and that's how it should be used. Failure. So you've got multiple instances of your data now distributed evenly amongst your data sets. Okay, a node goes down. In this example here, the previous master has gone offline. Okay, this immediately triggers an election process that goes on behind the scenes. Okay, so I describe the nodes as probably the most paranoid friends you can imagine. Continuously under the scenes, they're asking, are you there? Yeah, are you there? Can I see you? Can you see him? As soon as they go offline, as soon as the master is unavailable, an election process occurs, and one node gets elected, the master. That node's first task at hand is it promotes, because as we see, we've lost a primary shard in that node going down. Its first task at hand now is to promote a replica to a primary. Okay, so now it's got a primary shard. Now it can carry on writing for that data set, And also, more importantly, is that it creates another replica of that data. You've asked Elasticsearch your sharding policy. It will be maintained in the event of disaster. So the key characteristics here are replication, okay, data duplication. It provides you obviously your read scaling, okay, so as you have more demand, and it's providing you high availability. So as failure occurs, it's now handling. And sharding is data partitioning, okay. It's the way to partition large data sets over multiple machines, okay. So as your data set grows, you can have a sharding policy that will allow you to scale out to multiple machines. You may have a policy that has a limited number of machines to start with, but the idea is that once you have decided a sharding policy, we tend to kind of promote the concept of over-allocating, okay? So we say, I might need 5 shards, but I'll give it 7, okay? There's an aspect here where it allows you just to grow. It allows you to have more machines if and when your data grew, and then you could distribute those shards to physical different machines. Okay, so that's the kind of background for data distribution. But the other key characteristic of Elasticsearch is it's obviously this kind of robust, very detailed DSL for querying your data, okay? I just wanted to highlight here that there are many parts of the system we could be talking about, mapping, analysis, but I'm just going to focus right now on the kind of query DSL. Because there's some aspects here that are quite important to understand. So when we talk about the query DSL, there's 2 components to it. There's kind of the query element to it, but there's also filters that you can apply, okay? So what's the variation between these 2? Queries participate in the scoring system of relevancy within Elasticsearch. This is the basis of information retrieval, okay? Filters do not. Filters are binary questions. It's either it is a yes or a no. Does it match? Does it not? Okay. What we tend to say is that queries are to do with unstructured full text data. Filters are to do with structured exact values. Okay. And more importantly, from the performance characteristic, is one is cached and the other is not, by definition. And the key part with regards to when you build up these queries is that the filters are applied first and then the query is applied, okay? So what we're saying is that you have a data set that you've filtered. You've said, I want this dimension of my data. I've taken a subset of that data, and then I'll query inside of that data set, okay? Basic structure. Rather unexciting. Okay, so filtered queries, obviously you've got the 2 components now in the action here, okay? So the filter will be applied first, give me only active status, and then query within it for an unstructured piece of data. Okay, that's why it can be efficient. Some kind of, I guess when you come from kind of the SQL world, you know, trying to map terms and meanings to things, okay? So a where value is kind of maps similar to a terms filter. Obviously title brown, obviously it's a where clause. It allows you to kind of subset a segment of data. Where field in, okay, that's a terms clause with an array. So if it's in one of those values, then bring that subset data back. Keep on going with that kind of SQL-y feel to things. So where greater than and less than, okay? So we walk across a number of data types here. So we've got 2 sides here. You've got a range on a value, numeric value. Only find me data sets that contain a value in that value range. And it works also in data types as well. One of my favorite kind of filters, this is the kind of one you pull out your toolbox when you want to just when you can't really just get your data without having a good bool expression, okay? So what we have is this kind of a construct which you can put together. And it's called a bool because what we're saying here is that the must clause is like an and, okay? Should clause is an or, when clearly must not is not. And this allows you to create fantastically complex and rich requirements in how to extract a piece of data set out. And bools can be composed, so you can have a bool within a bool. So there's no end to the complexity you can get together. And to just give you kind of an example of, going to town, as it were, we can have a bool filter query. So what I see here is obviously we've got a range going on. Okay, so we've got a date range. So it must be in that date range. That's clear. The shoulds part is that it has to be one or the other. I don't care which one. One of those should be true. That gives you that kind of fuzziness to your search, so that I can say I'm looking for one or the other. I'm not going to try and narrow it down here. And obviously must not, it means a restriction of such set data. And the important thing to remember about this kind of construct is that we're caching this in the back end. Okay, this filter's being cached. And it's not being cached at the bool level. It's not being cached at that request that you just placed in. It's being cached at the individual elements. And the reason for that is that we want to maximize the reuse of these components that you've queried. So if you were to query that in a different term the next time, say for example you switch one of them out and added a different filter in there, then we've got 3 filters that we already cached, then there's a new one arrived, okay? It improves the reuse associated with caching by having these individual components. And you can change the order of them and have different queries coming in. So the other key characteristic we're seeing lots of use regarding Elasticsearch is aggregations. Okay, you've got your data in, you can search it, there's vast quantities of data, more and more is getting thrown in here. And people are asking it questions now using what we call our aggregations DSL. Okay. So there are different types of aggregations. Buckets. Buckets are the grouping behavior associated with aggregations. They don't do anything else except group sets of data specified by whichever type of bucket aggregation you've requested. So terms, for example, you might take your data set and say, run across this field value and aggregate around all the data that actually contains the same value. Date histograms, you can put date ranges, give me every minute, every hour, every daily. But you are creating kind of groups behavior of data. And the list goes on. We've got, I don't know, 15 plus. And the other aspect to aggregations is that once you have information grouped, then you can ask it questions that creates a value, as it were. Simple one like count. Once you've bucketed around these values, count how many is inside. Very easy. But we go on and on. We got stats, percentiles, cardinalities. You can find top values. Again, the list goes on and on. And it's the combination of these 2 feature sets that work with regards to aggregations. And they work at data volume, at scale. Just how you put them together. Buckets can be composed of other buckets. They're composed of other buckets. You can keep going in this terminology here. So what you're saying here is that you choose I guess your initial first level here. So you find a grouping behavior that expresses what you're looking for. And then within that, you can put sub-buckets. And then within those buckets, you can ask questions, okay? And this is the kind of analytical structure that we work with. We've changed the name here, AGS, that's what we call them. So just to give you an idea of how they're working here, okay? So you've got your data sitting out in multiple nodes, okay? Now, aggregations work in the same manner, in the same DSL structure, at the same level as your query, filter, you can have AGS, okay? So they're in line. They're executed on each shard, okay? And that's the key to scalability performance. There's a number of phases that go through to produce an aggregation. Okay, parse, collect, combine, produce. What does that look like? So just like any other request in Elasticsearch, you'll send it into a node within the cluster. That'll be called the coordinating node. It's its responsibility now to work out what to do with this request and who has this data that it has to call out to. So it takes this request, it splits it apart, finds out which data set it needs to be calling, and it sends them out to each individual shard that contains the data. Okay. It's their responsibility now to initialize data structures that represent the aggregations that you are requesting in the system. Each shard in isolation will be performing these actions. So it'll be performed in parallel. And the aggregations then get combined and then obviously sent back to the controlling node. Okay, so it's divide and conquer, effectively. Yeah. Obviously gets brought back together and as a single aggregation. Showing JSON in slides is never beautiful, okay? So you got some colors now. But this is the kind of structure what we're saying here. If you look here on the left-hand side, the request it sends out, okay? Here's a date histogram. That was a bucketing request. And within that bucketing request, we have this max temperature. It's using max, which is a metric request. So what we're saying is, please bucket up every day, and within that day, give me the max value of a certain field, okay? And then the response that comes back is a series of buckets that represent per day on your data set. Within those buckets, you'll have an attribute that represents your max temperature that you've requested. If you change the name from max temperature to something else, it'll come back with that something else, okay? But the key point is that you're asking a day histogram and max in combination. You could keep going. You could group many within this structure. Now, great feature. Love writing JSON myself. But if you don't like JSON, we have Kibana. Kibana 4 comes now complete with an aggregation engine inside of it and its click behavior. So we have an aggregation builder, which is basically WYSIWYG. Okay, you can play around with aggregations. Just point it at your Elasticsearch index, and then start exploring your data. Okay, get it wrong. It's not informative. You can just keep repeating the process, canceling it, and trying different aggregations and different visualizations. Okay, and then this what we're finding is that kind of people like kind of clicking through and exploring. And what you can do actually with Kibana, you can quite see these little arrows down in visualizations, is that once you've explored it with this visual tool, you can actually just copy the aggregation, use JSON structure out of it. It's there to be as a payload, and then put it programmatically into your code base, if that be your requirement. Okay, so finally, just kind of the comment being is that aggregations is designed to be efficient and performant at scale. Okay, it's ensuring that there's kind of single network round trip associated with collecting the data. I know where the data is. I go directly to it. Once we get that data loaded up, we're passing through at a single time. If you start monitoring your system and you're loading lots of aggregations up, you will notice it's using memory. It is in-memory computations to ensure that speed of the system. There are some use cases where some of these bucketing requests, we have to choose a speed over accuracy. Okay, I think this is an example of I think it's a cardinality is the key characteristic. So cardinality is using this kind of hyperlog kind of algorithm, which is statistically correct. Yeah, statistically, with a variance depending on how large a data set is. But it's a complex problem to solve there. Aggregations can be composed. So what you can do is that you end up creating dimensionality in your data and then layering it. And what we see with people using Kibana in particular is they create lots of informative visuals that represent their data. And they can see quite clearly what it represents once you have the layers and layers of aggregations over top of it. And the most important part of the system is the response time at scale, as close to real time. And that was it. I don't know if you want questions, answers now, or are we going to group them to the end? I'm not quite sure how this is going to structure.
It's up to you guys. Depends on what you want to do. Like,
yeah.
I don't know. If people will remember the questions after, we can just carry on.
Any questions?
Any burning questions that yeah?
You said before that the queries participate in the scoring mechanism.
That's correct.
How does the scoring mechanism work?
Well, I think I'll pass this one to my friend over there, who's our scoring mechanism master.
We have some out-of-the-box heuristics. Some of them are very, very old, actually. They date back to the 60s in information theory and Shannon and all that stuff. And this is like TF, IDF, and all these kinds of things. The way I normally describe it is the Lucene engine tends to like repetition of things. So the document repeats a term multiple times, got the word pizza in it many times, that's a good thing. So it must be really about pizza if it's got that word in it many times. That's where the whole keyword stuffing industry came from in SEO. They were trying to gain that part of the system. IDF is given 2 words, and we want this or that. We'd rather have the rare word than the common word, because it's just more discriminating. So TF, IDF, length normalization is another one. I'd rather match a document that was talking about me and just had my name in it, rather than the telephone directory full of all names in Manchester, because the probability is on those 2 words are bound to be in there somewhere. So length normalization, coordination factor, which is just basically, if you give me a whole bunch of search terms, I want documents that contain most of the terms you gave me rather than just one. So all these kind of go into the mix and they produce a score, and it works for most things, but we have a whole bunch of tweaks that you can apply on top of that to do things like, I want to boost documents based on the popularity field that's held inside there, the number of clicks that a page has got or something. I might use that as an artificial boost on top of the actual.
You can customize the scoring mechanism.
We have some default heuristics, but you've got it completely open to whatever scoring strategy you use.
Hi. You said when we do filter, filter will be applied first and query. Can you not reverse the feature? I have a query and set of results and apply filter on that.
How did you think the? Okay, let me ask another way. The filter would represent the same whether it was run before or after. It would extract or remove the same data set. It's just that the way that you've described, you've had to query a lot more data in order to get the same answer that we'd have returned when applying the filter first. Okay. So in other words,
it may not be the same answer.
So the filter is binary. So it's going to work, as it were, on the data set that comes back, regardless. So you're going to extract the same amount of data coming out of your system. So you get the same answer, as it were, coming back to the query. It's just less efficient doing it the other way around.
So what are the scenarios that Elasticsearch loses data? Is it like, is it production ready in a way that I need to back up Elasticsearch with another database, or is it like proven that there is like, or there are like known scenarios that we should consider when you're deploying Elasticsearch? Okay,
I mean it's a very topical question. Obviously, Elasticsearch came to this problem domain as a search engine. We were expecting people to re-index their data, have a primary data store. As time has passed, what we've done is that we've started to harden the system, moving it towards a data store. Okay, people are using it as a data store. So what we've done is we've put a lot of effort into ensuring, let's say, consistency of data as it transfers across the system. Okay, that's hugely important. Elasticsearch is moving data. It's copying replicas, machines go down, it's copying sets of data across. We've basically gone from the ground up in Lucene, we've checksummed everywhere data moves around. The other aspect is that as you're indexing data, and this is the key characteristic where you may lose data. When you're indexing data and you haven't flushed it to disk, it has potential to have lost information at that point. Okay, the machine goes down, it's in transit, gone. So what we've done is that we've built out a transaction log and made it durable in the file system cache, I believe, isn't it? And the idea being that we will be able to replay that data now as in the event of loss. For example, the machine goes down. So we're moving towards a scenario where we're narrowing down where potentiality of loss is. Okay, obviously we distribute systems. Distributed systems are complex. We do have an Elasticsearch page called the Resiliency page. Okay, it lists quite clearly all the ongoing effort associated with various aspects of potentiality of loss of data. Okay, I implore you to look at that page if you're looking towards using this as a data store. Sorry. The ongoing work is the fact is that because it's distributed and because we're hardening the system, we're finding a little few edge cases. We're going through testing it. We've got a chaos monkey in our test system that brings up and down nodes, brings networks off and on. And we're obviously got a huge customer base now who's coming to us and validating some of these requirements. If you're using it as a data source, do have a good backup schedule, like you would do with any other data source. I think there's a question coming up here.
Yeah, so you mentioned with the filter caching that you do it per expression.
Yep.
Is there any way to do it for a kind of filter query as a whole? Because I understand that it could add kind of memory, high memory usage by doing it per kind of expression, especially if you've got like quite a few permutations for each kind of expression and stuff like that.
Yeah. I guess the aspect here is that we do have a filter cache, but we also have we evict things that maybe haven't been used in a while. Okay, so we are maintaining actively a cache behind the scenes by evicting what we would call infrequent.
I mean, we have some heuristics which we think it's better to cache the leaves than the roots of your filter trees.
Right.
That tends to work out best. If you know more about what's cacheable in your system than us, then you can explicitly say this filter expression I want caching or don't want caching.
Okay, cool.
Yeah, I mean, there's bad candidates for filters. There's aspects like a very high cardinality field where every time you query, I give you a different value. Or the classic one is to query on a time element using now, which is millisecond precision. Yeah, it's not going to be cached for long. It's just thinking about your data. How reusable is that kind of filter? You can specify not to cache things. So if you know that a query is of poor cacheable characteristic, you can pass in an attribute to tell it not to cache. And I think we will find that ongoing, I mean, we don't want to talk about this, but we're looking in 2.0 to do a lot of this behind the scenes within Elasticsearch so that we decide, as it were, knowing the data, knowing the type of query, we'd make these choices on your behalf. Again, you can override, but that's the characteristic of 2.0. We're going to try and refine that so you don't have to think so much about it.
There's one more question. So I noticed that I wasn't aware of this, but I noticed that it doesn't have a query cache because I kind of assumed. I mean, Solar does. So
No, it does not.
It does not.
It does now.
All right, it does not. Cool. Right.
Yeah.
Right,
Shy recently added a query cache.
Sweet.
Yeah.
Sorry, I wasn't good. Cool.
Yeah.
Right.
Cool. Yep.
Buckets contain large volumes of data stored in memory. We have multiple queries running against the same sets of data repeatedly. Is there a way for us to cache those buckets?
Aggregations themselves, are they cacheable? So when you run an aggregation, will it be computing the aggregation each time you call it? My question.
It does.
Yeah.
Yeah, I mean, the hard thing is when to invalidate a cache. That's the tough thing. Filters are eminently cacheable because we know which files change, and we have caches built into each of the segment files at a very low level. When it comes to something which is an aggregation, which is a summation of lots of things, it's hard to know what ingredients that went into that might have been subject to some kind of change. So that's why they're recomputed every time.
So, and what's the offset? Are you seeing?
As I say, we run multiple queries against a very small subset of our large database.
Yeah.
And then we repeatedly run these, and we see that ramps up quite quickly.
Okay.
As we're running these data queries.
Yep.
Now, it tends to be a fixed amount of data that we're reapplying different filters to.
Mm-hmm.
And what we're seeing is we're seeing RAM load, and eventually Java falls over.
Okay. I mean, there's aspects if there's a common subset of your data, then one of the features I use normally is to create aliases into those data structures. So that dimension of data has a name. And that name is then what I aggregate across.
Recently implemented to try and get around the problem we're seeing.
Yeah, I mean, aliases are a really good feature of Elasticsearch. It's the ability to change your mind, effectively. So an alias is effectively an indirection to an index. Okay, you can give every index an alias, for example, and that's something maybe you pass out to your client APIs and out to your end users. What allows you to do now is that behind the scenes I can change my indexes, and then once I've changed them, flip the alias, and the people are none the wiser who are using your system. The classic cases are when you got time series data, for example, when you go into the Elasticsearch used in time series manner, which is maybe logs, and you've got logs churning in daily occurrences. You might have an alias that says today. Behind the scenes, there's an index with today's date in it. Today's always today. There's an aspect as the end user doesn't need to know. So you can use things like that to move aliases across last week. So you might have a bunch of indexes, and you can associate an alias to what last week represents. And these things you can just do in real time behind the scenes. That means you can change your mind. You can re-index data. Another great option is that you can behind the scenes re-index, make some changes, maybe change a different sharding policy, and then flip your index to use the new one. And your consumers are none the wiser because they're using an alias. So it gives you a lot more flexibility. Yeah.
Yesterday's the one.
Yes. Yesterday. Okay.
What use cases are there to use Elasticsearch? Where do you see your customers using Elasticsearch?
I don't know where to start. So you could go to your kind of Netflixes of the world that have hundreds of nodes of Elasticsearch, monitoring everything they have in the system. Okay, and that aspect, that's structured data. So they're looking at what's happening in the data centers and responding to it. You've got banks that are doing predictive analysis based on large data sets. One advantage of having large data sets is that you can ask a question. So you can say, what's happening today in comparison to last year, for example? You can perform, let's say, you can extract a foreground and ask the background what's different about it. Is it performing better? Is it worse? Where does it match in the heuristics of my data set? And you can do predictions based on that kind of actions. So that's one quite unusual use case. Classic search, GitHub, classic search. It's a mix of structured and unstructured. So you've got obviously repositories, and you've also got aspects about language. So that's kind of structured data. It doesn't change within a repository, or maybe have a combination of them, but that's the kind of aspect there. We handle geospatial searching as well. So there's an aspect that there are some sites now, I think, in classic examples, the Yelp or something.
Geosite, Foursquare was one.
Foursquare, yeah.
On the market.
On the market, yeah, okay. So we handle GeoJSON, GeoHash capabilities. What you can do is you can store a shape in Elasticsearch, and then you can ask your documents, bring me all the documents that match that shape, geographical shape, and out comes the documents. So what's near me? What does Manchester look like as a polygon? And then find an intersection of that polygon with my data set. So that's another aspect. And then obviously the analytics part. Some people are just using us for the analytics on top of structured data. And I guess what we're trying to say is once you handle structured and unstructured at volume, there's not many data structure types available to you after that. You know, there's maybe geospatial searching as well as structured and unstructured, but that's what it comes down to. Okay.
Okay.
Yep.
Yeah. So 10 minutes break and then the next topic. Yeah.
Cool.